So that by varying the R.
Yes, sir.
I completed that, and also I completed the maximum utilization factor, and also the blade speed ratio for axial as well as for radial. Even this also completed. Okay, I think I completed when VU1 and VU2 are in opposite direction. Okay, so we'll get power equation or the energy transfer equation as VU1 plus VU2. And next, if VU2 is in the same direction of VU1, okay, so this is the velocity triangle, and whatever the power or the energy equation or the work done equation, we'll get VU1 U1 minus VU2 U2, and here you can see the directions. Okay, here you can see the directions. Okay. Next, similarly, we'll go for if the fluid enters axially or radially in case of axial or radial missions. Okay, please understand here. Okay, because while solving the problem, okay, these conditions are very important. Okay, and the notations are also very important. Okay, so here, what is the condition? If the fluid enters, okay, the fluid enters is nothing but it is an absolute velocity v1 at inlet. Okay, if the fluid enters axially or radially, axially or radially is nothing but it is in a perpendicular. Okay, it is an a perpendicular. Okay, it is an a perpendicular in case of an axial or a radial flow missions. Okay, so here we can see how to draw the velocity triangle for this. Okay, so I'll come for here. Okay, I'll come for here. So just I'm going to draw the basic velocity triangle here. Okay, so I'm going to draw the basic velocity triangle here. So at inlet. Okay, I'm going to draw at inlet. So this I'll call it as an a VR1 with respect to beta. So next I'm going to draw here alpha 1 and this is V1. So alpha to beta, so I'm going to call it as an a U1 Next, from year to year, we can call it as an VU1. Okay, and this is relative velocity VR1. Okay, what is the condition? What is the condition? So the condition they given, if the fluid enters axially or radially. Okay, axially or radially. So the fluid enters means whatever the absolute velocity v1, okay, whatever this absolute velocity v1, okay, so the fluid is entering axially or radially. Axially or radially is nothing but whatever the flow here, okay, direct rate will come to here. So once again I'm going to draw here the basic velocity, sorry, as per the condition, the velocity triangle. So this the same velocity triangle I'm writing. So this I will going to call it as an a VR1. But as per the condition, if the flow velocity, if it is an axially or radially, so this one perpendicular. Okay, axially means okay on this line. Okay, perpendicular means okay it is in a 90-degree. So this I'm going to write here itself. So this angle will become alpha 1. Okay, so VR1 is equals to V1. Okay, VR1 is equals to V1, and I'm going to write as it is. So whatever this, I'm going to call this as an a VR1, and this angle is beta 1. And say if this is the alpha 1, okay, if this is the alpha 1, from this to alpha to beta, we will get U1. Okay, now my question is, what about VU1? Okay, now my question is, what about VU1? Okay, anyone, you can tell. What about VU1? What about VU1? What about VU1?
Sir, explain once again, sir. Did not understood.
Sir, can you explain this concept once again?
See, last class I completed up to here. Okay, last class I completed up to here because clear cut I told, okay, if you understood how to draw the velocity triangle, see, this is the hints. Okay, this is not in your syllabus. It is not a part. Okay, it is not a part. Okay.
Okay, sir.
Once again, if you're asking me, say, I will explain. Okay, there is a no interaction. Then why should I do all this?
Yes, sir.
Yeah, okay, first I'll come for. So hints to draw the velocity triangle for given condition and other aspects related for solving problems. Okay, so the equation, whatever this given u1 and u2, we can call it as it is a blade speed velocity. Okay, u1 and u2, it is a blade speed velocity with respect to inlet as well as outlet. Okay, one indicates it is an inlet, two indicates it is an outlet. Okay, but here they given for axial flow type. Okay, axial flow type means whatever the diameter, okay, or whatever that radius, okay, it is falling on the same line. Same line is nothing but parallel to that axis. So that's why d1 will become d2. Okay, d1 is equals to d2. So that's why u1 will become u2. So we will get pi dn divided by 60. Suppose if we have the different radius or different diameter d1 and d2, so we'll get the formula u1 is equals to pi d1n divided by 60, u2 is equals to pi d2n divided by 60. Okay. Next, second one, if the machine is of impulse type. Okay, impulse is nothing but in this, the pressure is constant. So if the pressure is constant, whatever the relative velocity, okay, VR1 will become VR2. Okay, so the relative velocity is same as at outlet. Okay, so already we discussed in by varying the r. If r is less than 0, what is the condition? If r is equals to 0, what is the condition? So if r is equals to 0, okay, so we will get impulse type mission. So in that relative velocity is same as at relative velocity at outlet for ideal cases. Next, similarly for if the mission is of 50% reaction, okay, if it is in a 50% reaction, so R is equals to 0.5. So that also in the last class we discussed. Finally, we will get the condition V1 is equals to VR2. Okay, V1 is equals to VR2 means I will talk with respect to angle. V1 is nothing but, okay, nozzle angle alpha 1 is equals to VR2, blade angle at outlet. So it is in a beta 2. And V2 is equals to VR1. So V2 with respect to angle alpha 2, VR1 is nothing but it is an a beta 1. So here I shown. So alpha 1 is equals to beta 2, or I will call it as an a V1 is equals to VR2 and alpha is equals to beta 1. So V2 is equals to VR1. So symmetrical blade conditions only. Okay. Next, for radial flow missions, the fluid enters at radius R1 and leaves at radius R2. So here only I discussed. If we will get the different radius, so whatever the blade speed velocity, okay, U1 does not is equals to U2. Okay. Next, while coming to here, if the tangential component of absolute velocity, so what is the tangential component? So VU1. Okay, so while writing the velocity triangle, okay, so I'm not discussed this uh, directions, okay, but right now I'm discussing the direction. The reason is while writing or while solving the power equation or the energy transfer equation, okay, so whatever this, so up to here we discussed E is equals to VU1 U1 minus VU2 U2. Okay, but see here I written positive. So y means, okay, so while coming to the tangential component of absolute velocity, okay, so v1 is the absolute velocity, okay, so component, so this is vu1, okay, and another one is vf1, but right now vu1, okay, and vu2, okay, are in a opposites. Okay, if these two are in a opposite directions, why this is a opposite direction means, why this is opposite direction means, okay, I'm going to show once again here. Okay, you just see this is, so I'll call this as an a v1 and this is vr1. So with respect to outlet, so this is vf2 and this is v2, this is vr2 with respect to angles. Okay, with respect to angles. So initially while drawing the inlet velocity triangle, okay, so that directions, okay, the direction means suppose the nozzle is present here. Okay, so I'm talking about the nozzle is suppose present here. The fluid is flowing in this direction with an angle alpha 1. So this I will call it as an absolute velocity. In which direction? So in this direction only. Okay. So but what about VU1? So VU1, okay, it is moving from left to right. Okay, it is moving from left to right. Okay, similarly at outlet, suppose if this is the blade, okay, suppose if this is the blade, okay, this is the blade, so outlet will get here. Okay, the outlet will get here. So I'll take this velocity triangle. Okay, I'll going to take this velocity triangle. Got it? So in which direction? So from here to in this direction. So from bottom to upward direction. Got it? So we will get, so this is the beta and this is alpha. From alpha to beta, we will get U2. From alpha to VF, we will get VU2. So VU2 is in which direction? So it is in the direction of right to left. Okay, right to left. See, like this. Okay, suppose this is the water outlet, means in this direction. So now you check. Okay, now you check. So VU2, so VU1 as well as the VU2, when these two are in a opposite direction, then the power equation or the work done equation, I will going to write. So VU1, U1 plus VU2, U2. I hope you understood this. I hope you understood this.
Yes, sir.
Hmm?
Yes, sir. Yes, sir.
Yes, fine. So the same I written here. VU1 and VU2 are in a opposite direction to each other. The equation in evaluating either power or energy transfer becomes P is equals to, or E is equals to, or W is equals to. So VU1 U1, it is in a plus VU2 U2. Okay. Next, another one. If VU2 is in the same direction of VU1. Okay, if VU2 is in the same direction of VU1. Okay, so when we will get this condition? See, initially, just now I discussed this one. Suppose while solving, okay, I'm discussing here itself. Suppose while solving, if you are getting VU2 as a negative value, okay, suppose if you will get VU2 as a negative value, then we have to modify the outlet velocity triangle. Okay, then we will going to modify the outlet velocity triangle. Okay, so how we will going to modify the outlet velocity triangle? In this manner. Okay, initially in this direction. Okay, so VU1 and VU2 in opposite direction. Okay, but if we'll get VU2 as a negative sign, okay, then we have to modify the velocity triangle. So we have to modify it in this manner. So then the direction will become, see, left to right. Okay, the direction will become left to right. So when we have to modify the velocity triangle, when VU2 will become, okay, when VU2 will become negative sign. Got it? Got it? So then the equation will become P is equals to VU1 U1 minus VU2 U2. Okay, so if you have any doubt, okay, so I'll going to explain once again if you want. See, this is the first condition, the general velocity triangle. Okay, but power equation is VU1 plus VU2 into U. But here it is in a negative sign. Why it is in a negative sign? While solving the problem, suppose we are getting VU2 as a negative sign. Okay, then this is the velocity triangle. Later we have to modify to this velocity triangle. Then the direction will become, okay, left to right. So then VU1 minus VU2. I hope you understood this condition also.
Yes, sir.
No?
Yes. Yes, sir.
Clear? So only the reason is negative value of VU2. So then the power will become negative sign. Okay. Yes. Next, we'll come for if the fluid enters. Okay, if the fluid enters axially or radially in case of a axial flow or a radial flow missions. Okay, so now my question is, okay, what is this fluid enters? Okay, what is this fluid enters? In which notation we can use for this, for fluid enters? The fluid is entering into the turbine. So which notation we can use? Which notation we can use? I'm not discussing, I'm not talking about the velocity triangle, but the fluid enters. So which notation we can use? I'm audible? I'm audible?
Yes, sir. Audible, sir.
Yes. So which notation we can use for this fluid enters? I'm getting the answer from only one. Okay. So I only discussed. Say fluid enters is nothing but it is an absolute velocity v1. Okay. If the fluid enters means, okay, so it is an absolute velocity with respect to alpha. Okay, with respect to alpha. Okay, so if the absolute velocity, okay, is entering axially or a radially, okay, axially or a radially, in case of a axial flow type missions, or it is an a radial flow type missions. Okay, so I'll going to show here. I'll going to show here. So initially I'm going to draw the velocity triangle here. So this is the reference velocity triangle at inlet. So this is alpha 1 with respect to absolute velocity v1, and this is blade velocity vr1 with respect to angle beta 1, and this is the flow velocity vf1. So from here to here we can call it as an a u1. Blade speed velocity from here to here it is an a vu1. Okay, the condition is the fluid enters, okay, is axially or a radially. See, this is the fluid entering absolute velocity with respect to nozzle angle alpha 1. Okay, it is an a nozzle angle alpha 1. So I'll going to draw the velocity triangle once again here as per the condition. See, this is vf1, the flow velocity. Okay, but what is the condition? The condition is the fluid enters axially or a radially. Axially is nothing but we know. So if the water is flowing, okay, so the axis of the rotation, it is in a parallel to that axis of the rotation. So here I'll going to write. So here I'll going to write the V1. So VF1 is equals to V1. VF1 is equals to V1, and this is beta 1 and VR1. And whatever this angle, I'll call this angle as alpha 1. Why? Because see, whatever this absolute velocity, okay, it is an axially or a radially. Axially or a radially is nothing but see this one. Okay, whatever this V1, okay, V1 is falling on VF1. The reason is the fluid is entering axially or a radially. Okay, so that's why I written VF1 is equals to V1. Okay, next, whatever this V1, sorry, whatever this U1, okay, it is coming to this. So alpha 1, sorry, alpha to beta, we can call it as an U1. Now my question is, what about VU1? Now my question is, what about VU1? What about VU1? So for VU1 there is an any value. So here I written already VU1 is equals to 0. Why it is 0 means, okay, so I'm going to draw here. So right, VU1 is equals to 0. Why VU1 is equals to 0? Because see, from this distance to up to this distance, okay, from this distance to this distance, okay, so this V1 absolute velocity is falling on VF1. If absolute velocity is falling on V of 1, okay, there is a no whirl. Why there is a no whirl means, Okay, because the flow is itself, okay, it is an axially or a radially. So that's why the viral velocity at inlet is 0. Okay, I hope you understood this condition.
Yes, sir.
Yes or no?
Yes, sir. Understood, sir.
Yeah, fine. Thank you. Okay, next we'll come for, so another possible velocity triangle. If the blades are radial, okay, so in sixth condition, the fluid enters means with respect to absolute velocity v1 and nozzle angle alpha 1. Okay, now my question is, what about the blades are radial? What are the blades are radial? See, here the blades are radial is nothing but, okay, so I'll take this condition. So once again, I'll going to draw the velocity triangle here. So this is the base velocity triangle or a reference velocity triangle. So this is the inlet velocity triangle. Still we are talking about the inlet velocity triangle. So this I'll call it as an a VF1. So this I'll call it as an a VR1. And this I'll call it as an a alpha 1 absolute velocity. From this distance, I'll call it as an a U1. From here to here, I'll call it as an a VU1. And this angle, it is an a beta 1. This angle, it is an a beta 1. Okay. See, the condition is if the blades are radial. Okay, blades are radial means, okay, please always you remember, okay, VR1, it is an a relative velocity, and B1 is, sorry, beta 1 is nothing but it is an a blade angle. Okay, it is an a blade angle. Okay, so the condition is the blades are radial. The blades are radial is nothing but, okay, whatever this relative velocity VR1 line, okay, with respect to blade angle, okay, it is lying on VF1. Okay, VR1 with respect to blade angle beta 1, okay, it is lying on VF1. So here I'm going to draw as per the condition. So this I'll call it as an a VF1. So this is VF1. Okay. So this relative velocity, because the blades are nothing but moving blade angle beta 1. Okay, with respect to relative velocity. So this is the blades are radial at inlet is nothing but, so VR1 is lying on VF1. So we can write it as VF1 is equals to VR1. Okay, then what about this angle? What about this angle? So this angle, it will become 90 degree. So beta 1 will become 90 degree. The reason is the blades are radial. Radial is nothing but perpendicular. Okay, so beta 1 is equals to 90 degree. And I'm going to write as it is as a V1. So this is V1. And this is alpha 1. See, from alpha 1 to this, I will call it as an a U1. But the distance, now you are going to check from alpha to beta, it is an a U1. Again, from alpha 1 to VF1, it is an a VU1. Okay, this, whatever the absolute velocity, it is not falling on here. Okay, which one is falling? The relative velocity or the blades are radial means So we will get V1 U1 is equals to VU1. U1 is equals to VU1. Clear? I hope you understood even this condition also. If the blades are radial at inlet.
Yes, sir.
Clear?
Yes, sir.
Yes. Thank you. Next, the combination, not a combination. If the fluid leaves axially or a radially. So once again, okay, I will discuss like that only. Fluid leaves. Fluid leaves is nothing but you just tell with respect to velocity. With respect to velocity. Sixth one, the fluid enters. Fluid enters means absolute velocity V1. Here the fluid leaves axially or radially. Okay, the fluid leaves is nothing but it's an outlet. Okay, axially, radially in a axial or radial flow type machines. Okay, so for this, I'll going to discuss here only. Okay, if it is an outlet. Okay, if it is an outlet, okay, so once again you're going to draw outlet velocity triangle here. So once again I'm going to draw the outlet velocity triangle here. So this I'll call it as an a VF2 and this V2 and this VR2. So alpha 2 and this is beta 2. Okay. So I'm going to take this condition here. So condition is the fluid leaves axially or a radially. So I will going to take this V2. Okay, the fluid leaves axially or a radially. So then this line, okay, it is falling on VF2. So once again, I'm going to draw as per the condition. Okay, at outlet. So this is VF2 and whatever this V2, okay, it is falling on VF2 because the fluid is leaving axially or radially. So this angle I will call it as an a alpha 2 and this remains same. So I'll call it as an a VR2. So this is VR2. So this angle is beta 2. So from here to here, it is an a U2. But once again, VU2 is equals to 0. The reason is there is a no whirl because the absolute velocity itself is an a perpendicular. Okay, so the absolute velocity itself perpendicular. So there is a no whirl velocity at outlet. So that's why VU2 is equals to 0. Okay, I hope you understood even this condition also. If you understood inlet, the outlet is same. Okay, but yeah, with respect to outlet velocity triangle, you have to draw. Clear? So next I'll come for if the blades are radial at outlet. Okay. So if you understood inlet velocity triangle, okay, the similarly at outlet velocity triangle, but the condition is the blades are radial at outlet. Okay, the blades are radial is nothing but, so whatever the relative velocity VR2, okay, it will become perpendicular. Okay, it will become perpendicular. So then beta 2 is equals to 90 degree and VU2 is equals to U2. Okay, VU2 is equals to U2. So these are the possible velocity triangles and I given 10, 11. Okay, so it is a combination. Okay, it is a combinations. So these are the possible velocity triangles. Okay, while solving the problems you may get. Okay. So I hope you understood.
वेदांत आलेला आणि घेऊन गेला हा ते बेल्ला दिलो 5 बेल्ले दिलो
You want break?
आणि 2 ते होते ते पाण्याचे
You want break?
6 आहेत किती पाहिजे तुला
Yes, sir.
Okay, I'm going to start 1 o'clock. So, so please take book and all.
Yes, sir.
Okay. So before that, okay, just note down these equations. Okay, formulas used for the turbines, even in for pumps and blowers. So tangential force, so Ft is equals to, so m into Vu1. So it is a plus or minus. Why it is a plus or minus means, okay, there is a directions. Okay, so whether Vu1 and Vu2 it is in the same direction or it is in a opposite directions. So that's why is there a plus or minus Vu1 plus or minus Vu2. Next, for axial or radial thrust. Okay, so one is an axial component, so another one is a tangential component. So tangential means Vu1 and Vu2. Similarly for axial, okay, so we can write it as a Fa or FRD. So it is a m into Vf1 minus Vf2. Okay, so axial thrust. Please remember, so absolute velocity components, okay, there is a two components. One is a tangential component, so tangential force Vu1 and Vu2. Axial component, so our axial thrust, we can call it as an m into Vf1 minus Vf2. Similarly, torque T is equals to, so it is an m into Vu1 R1 plus or minus Vu2 R2. Okay, so here you can see in all the formulas there is a GC. GC is nothing but it is a unit conversion factor. Please remember this. Okay, so GC is nothing but it is a unit conversion factor. So always we're going to write it as a kg meter per Newton second square. Please remember this. Okay. So next, energy transfer. So we can denote it by E or generating head or W. So it is an VU1, U1, so plus or minus VU2, U2. Suppose if it is an axial flow, so U1 will become U2. So then U into VU1 plus or minus VU2. Or this is the alternate form of Euler's turbine equation. Okay. So or we can write it as, so another equation, E is equals to W V1 square minus V2 square divided by 2 into 1 minus R. And another formula is power output. So power output is P is equals to, so M into E, or the mass flow rate into work done, or we can call this an M into generating head, or M into delta H, so enthalpy. Okay, or enthalpy. So either we can use this notations. Okay, this notations. So next, degree of reaction. Okay, already we know we used, and utilization factor epsilon. Okay, and finally the relationship between. So while solving the problems, suppose if you want to find out the utilization factor, if we know the degree of reaction R, so we can use this formula. So epsilon is equals to V1 square minus V2 square divided by V1 square minus R into V2 square. So these are the formulas. Okay, so we're going to use in the problems. Okay, we're going to use in the problems. Yeah. First, I'm going to solve. So please note down this problem. Note down this problem. So liquid water flows at the rate of 31.5 kg per second through the rotor of a turbo machine, where inlet and outlet mean diameters are 12.5 centimeter and 20 centimeter respectively. Inlet and outlet mean diameters are 12.5 centimeter and 20 centimeter respectively. The other data relating to the turbo machines are speed is 6000 rpm. Speed is 6000 rpm. Absolute velocity of fluid at inlet is 35 meter per second. 35 meter per second, and is directed axially. So this is very important here. Okay, this is very important here. So absolute velocity of fluid at inlet is 35 meter per second and is directed, means it is entering axially, means here alpha 1 will become 90 degree. Okay, so alpha 1 will become 90 degree. If alpha 1 will become 90 degree, okay, so we will get Vf1 is equals to V1. So this is very important here. So continue. The absolute velocity at outlet is 160 meter per second. Absolute velocity at outlet is 160 meter per second and makes an angle of 30 degree with respect to tangential direction using the mean inlet and outlet diameters determine torque, so enthalpy across the rotor, and power in kilowatts. Draw the inlet and outlet velocity triangles. Draw inlet and outlet velocity triangles. To finish the statement.
Yes, sir.
Yeah, okay. So first, while coming to here in the problem statement, so they given the flow rate, liquid water flows at the rate of 31.5 kg per second. So they given M as 31.5 kg per second through the rotor of a turbo machine, where inlet and outlet mean diameters are. So here they given what is the inlet diameter and what is the outlet diameter. So it is not an axial flow. Okay, so D1 is 12.5 centimeter and D2 is 20 centimeter. Okay, next, the other data relating to the turbo machines are the given speed as 6000 RPM. Next, the absolute velocity of the fluid. So absolute velocity notation is V1 is 35 meter per second and is directed. Okay, is directed axially. Okay, it is directed axially. So axially is nothing but it is in a perpendicular. So the fluid enters axially or a radially. So V1 will become VF1. So then alpha 1 is 90 degree. Next, absolute velocity at outlet is 160 meter per second. So absolute velocity outlet means V2, 160 meter per second, and makes an angle of 30 degree. So the outlet angle, okay, so that is alpha 2 is 30 degree. So we have to find out what is the torque, okay, and enthalpy change. So that is the energy, and what is the power in kilowatts. Okay, so here the first thing is we have to draw the inlet and outlet velocity triangle, because for velocity triangles, okay, they will going to award the marks. So it is for 3 to 4 marks. Okay, so first, as per the condition, okay, draw the velocity triangles. Okay, as per the condition, draw the velocity triangles. Okay, or in the basic form, write the velocity triangle. So here the inlet velocity triangle as per the condition, okay, I drawn here. Okay, as per the condition is whatever the water is entering at inlet is axially. So that's why V1 will become VF1. So I written right angle triangle, and here VU1 will become 0. And VU outlet velocity triangle same. Okay, I written here. Okay. So next, the first thing is, okay, so if we know D1 and D2 and speed, so find out what is the blade speed velocity at inlet as well as the blade speed velocity at outlet. Okay, so find out what is blade speed velocity U1 at inlet and U2 at outlet by using this formula. Okay, so U1 we got 39.27 meter per second, and U2 we got 62.8 meter per second. Okay, so please calculate along with me. Okay, if you'll get any doubt, you just raise a point. So completed. If you'll get any doubt by drawing the velocity triangle, okay, you can ask. Okay, Neeraj completed.
Yes, sir.
Okay. Yeah. Next, from outlet velocity triangle, because see, anyway, VU1 is 0. Okay, we have to find out torque. For the torque, we know the formula. Okay, it is an m dot into VU1 R1 minus VU2 R2. Okay, vu1 r1 minus vu2 r2 into m. So that is the torque. For that, okay, we want what is vu2. So vu2 will get from the outlet velocity triangle. Okay, outlet velocity triangle. So we can use cos alpha 2. Okay, so cos alpha 2 is adjacent. Okay, so adjacent by hypotenuse. Okay, so adjacent vu2 and hypotenuse it is v2. So cos alpha 2 is vu2 by v2. So we can find out what is vu2. So we'll get the vu2 value as 138.56, and we know what is alpha 2 because clearly they given the angle at outlet. Okay, nozzle angle at outlet. So then write the torque equation and substitute. So in this vu1 is 0 because the fluid entering at inlet is itself axial, so that's why vu1 will become 0. Then find out what is torque. Then find out what is torque. Okay, got torque as minus 436.5 Newton meter. See here I written directly. Okay, because here we substituted already. Okay, GC. Okay, GC it is unit conversion factor, because without unit conversion factor, okay, we won't get Newton meters.
Sir, what is that 31.5?
Which one?
Saying that the torque equation.
See, 31.5 means what is your M? Flow rate.
Yes, sir.
Water
Yes, sir.
flows at a rate of 31.5 kg per second.
Yes, sir.
Okay.
And that 0.1 is the conversion factor.
No. 0.1 is it a radius, no?
Radius.
R2.
Yes, sir.
So they given in the diameter. Okay, they're given in the term of a diameter. So I want radius means it is in a 10 centimeter.
Yes, sir. Done, sir.
Okay. So you completed up to power?
Yes, sir. Complete, sir.
Yeah, okay. You got the same?
Yes, the same answer.
Yeah. So here it is indicating negative sign. Okay. So in the energy equation itself, okay, we are getting negative sign. Okay. Once we got the negative sign, so that type of mission we can call it as a power absorbing missions. Okay, it is not a generating. Okay, once we'll got positive, then we can call it as an a power generating turbo machines. But here, because we got the negative sign, so negative sign indicates it is an a power absorbing, whether it is an a pumps or it is an a compressors.
Sir,
Okay,
in that power, if we divide by 1000, we are getting 0.274.
it is a kilowatt. No, we are converting into kilowatts.
Yes, sir. If we divide, we get 0.274 kilowatt.
Yeah, correct.
So we have written 274.05.
274. Okay, fine. So means if you convert into kilowatts.
So directly, if we solve that,
Oh, directly. Okay, fine. Okay,
we are
fine.
getting
Okay. Okay,
0.274.
I will correct in my notes. Okay.
Yes, sir.
Thank you. So negative we are getting, so that we can call it as it is a power absorbing turbo machines. Okay. So next, we'll go for another problem. Next, we'll go for another problem. So the velocity of fluid flows from the nozzle is the velocity of fluid flow from the nozzle is an axial flow impulse turbine. An axial flow impulse turbine is 1200 meter per second. 1200 meter per second. The nozzle angle is 22 degree. The nozzle angle is 22 degree. The nozzle angle is 22 degree. If the rotor blades are equiangular, if the rotor blades are equiangular and the rotor tangential speed is and the rotor tangential speed is 400 meter per second. 400 meter per second. Find the rotor blade angle, tangential force on the blade ring, tangential force on the blade ring. Third one, power output. And fourth one, utilization factor. Utilization factor. Assume VR1 is equals to VR2. Assume VR1 is equals to VR2. Assume
Sir,
VR1 is equals to VR2.
excuse me, sir.
Yeah.
Sir, in the previous problem, that second answer, sir, for delta H naught. Sir, if we multiply that 138.56 into 62.8, we are getting like 8701.56. Sir, you have written 8.7 joule per kg. Means you have converted or directly written, sir?
This one converted, no. The problem is because see, here I written 8.7. Okay, so I should not multiply this, right? means
Divide.
1000.
Yes, sir.
Yes, yes, correct, correct. I will correct in my notes.
Yes, sir.
Okay. So then here we are getting 0.274.
Sir, no, if
It
we,
is in a watt.
say if we remove that 1000, we are getting point, then directly this answer is correct, sir. If we did not
Okay.
divide by 1000.
I'm audible? I'm audible?
Yes, sir, audible, sir.
Okay, due to internet problem, I rejoined.
Yes, sir.
Okay, you just find you completed this.
No, no, sir.
Okay. I'll wait. So from inlet velocity triangle, we'll get VU1 as 112.62 meter per second. By using this, by applying the Pythagoras rule, so find out what is VF1. So that is V1 square is equals to VF1 square plus VU1 square. So the VF1 value is 449.58 meter per second. So finished.
Yes, sir, finish, sir.
Yeah. So next we want to find out what is the blade angle. For that blade angle, okay. So just I will come for this velocity triangle. What is tan beta 1? So tan beta is opposite by adjacent. So what is opposite? So it is an a VF1 by this distance. So what is this distance? So VU1 minus U1. Okay, the distance is VU1 minus U1. So we will get tan beta 1. So tan beta 1 is opposite by adjacent. Okay, by using this, find out what is the beta 1 angle. Because in the statement itself, they given it is an equiangular. So we got beta 1 as 32.24. So we got beta 1 as 32.24.
Done, sir.
Okay. Next, find out what is relative velocity by using the same from the inlet velocity triangle. So substitute what is sine beta 1. ಈ ಕಡೆ ಕ್ಲೀನ್ ಮಾಡ್ತೀರಾ ಆಮೇಲೆ ಮಾಡ್ತೀರಾ So find out what is relative velocity. Okay, find out what is relative velocity. So find out what is relative velocity. See, from the inlet velocity triangle, so opposite by hypotenuse. relative velocity, so 842.57 meter per second. Why VR1 is equals to VR2 means because it is an impulse turbine. Okay, it is an impulse turbine. Completed.
Yes, sir.
So up to where you completed?
Sir, VR1.
Yeah. Okay, got the same.
Yes, sir. Same, sir.
Okay. So next, from the outlet velocity triangle, we have to find out VU2. Because why we require VU2 means, okay, we have to find out what is the tangential force. Okay, we have to find out tangential force. So again, from the outlet velocity triangle, okay, so what is cos beta 2? So find out what is this VU2 value. So cos beta 2 is adjacent by hypotenuse. So you'll get a VU2 plus U2 divided by VR2. So you'll get VU2 as 312.66 meter per second. So next, find out what is tangential force, Ft. So here we written tangential forces M into Vu1 plus Vu2, because why it is in a positive means, see, whatever Vu1 and Vu2, it is in a opposite direction. Okay, if it is in a opposite direction, we will get positive.
Done, sir.
So tangential force. Next, so we have to find out what is power developed. Okay, we required what is power. So in this, so we can write M into Vu1 U1 plus Vu2 U2. Again, Y plus means Vu1 and Vu2, it is in a same opposite direction. So it is in a axial flow. Okay, axial flow impulse turbine. So U1 is equals to U2. So that's why we took U M into U Vu1 plus Vu2. So we'll get, and here they not given the flow rate. Okay, they not given the flow, so that's why we're going to assume it is an 1 kg per second. 1 kg per second. So we'll get P is equals to 570.1 kilowatts.
Done, sir.
Okay. So next we have to find out utilization factor. Okay, we have to find out utilization factor. So we know the equation for relationship between utilization factor and degree of reaction. So we can use this equation, or no sir, directly I will going to use utilization factor equation. No problem, we can use that also, and you can find out. Okay, you can find out what is the utilization factor value. So here I'm going to use epsilon is equals to V1 square minus V2 square by V1 square minus R into V2 square. R into V2 square. So we can use this equation and we can find out what is utilization factor epsilon. But the problem is, okay, but here the problem is we don't know what is V2. Okay, here we don't know what is V2. So first we have to find out this V2, then we have to find out, okay, what is the utilization factor epsilon. So from the outlet velocity triangle, so apply Pythagoras rule. From outlet velocity triangle, apply Pythagoras rule. So find out what is V2. And you can, sir, you can ask why R is 0 means because it is an impulse turbine. Okay, it is an impulse type. So R is 0. So completed.
Yes, sir.
Yeah, okay. So you'll get epsilon as 0.79. Or simply we can call epsilon is equals to 0.8. Okay. So your IA portion is up to today class as FM part. Okay. As FM part up to today's class. Okay.
Sir,
So
show the
just
last
go through.
last
Which
equation.
one?
The last equation, epsilon, sir.
This equation, okay. Epsilon is equal to
Yes,
V1
sir.
square minus V2 square divided by V1 square minus R into V2 square.
Yes, sir.
Okay. So your IA portion, my part. Okay. So up to today's class. Okay. So you go through some more problems. Okay. You go through some more problems. And the pattern is one question from FM and another question from FP and one more question. So it is both combination. One question from FP and another FM. Okay.
Yes, sir.
Thank you.
Thank you, sir.